Before we begin with specific examples of implementing this kind of a formula and calculating electric fields, there were two observations I wanted to make about the electric field that will be useful before we begin into calculations. The first has to do with the fact that there is a Cartesian form for the force on charge capital Q, but there's also a trigonometric form. There's that trig form that we had used to derive our result in the previous example. Now, just like you have two choices for computing forces, you might suspect there is another choice for calculating electric fields based on the trig form. And sure enough, the way we would derive that is just how we derive the Cartesian form. We would write out exactly the same formula, but we'd write down the trig form version of it. And every single term in there is going to have a factor of capital Q, which we will factor out of the sum, leaving then just the electric field. So that another formula for the electric field is to simply write down the trig form for the force on charge Q while sitting at this location R. But as we write it out, to remember to not include the factor of Q, capital Q, which had already been factored out. So as we write down the trig form, we would have Coulomb's constant. We would have the product of the two charges in the numerator, but now we only have one charge in the numerator. The capital Q charge has been factored out of the sum. We have to divide by distance squared in the trig form, so that's Rn squared, where here by Rn I mean specifically the distance from charge number n, the general term in the sum. Rn is the distance from there to the location capital R, location lowercase vector r, where I'm actually calculating the field. And then finally, the trig form, you'll recall, requires a unit vector, r hat, and that unit vector should point in the direction along the line that connects the charge, which is the source of the field, to the point where I'm calculating the field. That vector, then I will also call r hat subscript n, where r hat n simply means that unit direction going from charge n off to charge Q, which would be sitting at location R. So it goes from Rn pointing towards location R. This then gives us the trig form, which is another option we have then for calculating the electric field. The final observation that I want to make has to do with the direction of the electric field. It's very important, or it's very useful, actually, for us to be able to guess at or have some intuition for this electric field. It is a vector after all. We want to know how to know in what direction it points for any given set of conditions. Now the key to that is to think about what this formula tells us. Now notice, this formula is telling us that the electric field at location R is some specific property of space at that particular location. So actually, I should emphasize, I want the direction of the field at a particular point in space. And what the formula is telling me is that if I were to put a charge Q at that location R, there would be a force on that charge Q, and the force would be, when I look at this vector equation, in exactly the same direction as the electric field, provided one condition obtains. It's very important that the charge actually be positive. If I have a negative charge here, that negative sign in this vector equation would make the force vector point in the opposite direction from the electric field vector. So as long as we consider a positive charge, we can imagine putting it at that location in space. We can then use our intuitions to figure out the direction that the force of what the force would be on that small positive charge, and then that automatically, through this equation, tells us the direction of the electric field. And the placement then of this imaginary positive charge at a given location, this is a concept known as a test charge, a small positive test charge. So to determine the direction of the electric field, direction of the electric field, it is the same direction as the force on a, and it's very important that we emphasize, positive test charge. Now normally we call our charges Q, But to emphasize that this has to be a positive test charge, I'm going to call it P for positive. It is the same direction as the force on a positive test charge P when placed at location R. And there's a little proviso here, provided the actual charges in the system don't move. In other words, sometimes we make the mental mistake that, okay, I want to know the electric field, say at some point, over here. I want to know the electric field there. And I imagine I put a positive charge there. Depending on the problem I'm solving, I might mistakenly think that these other charges might move in response to my placement of the positive charge. One way people handle that is to insist that you put a small positive charge there, so that if it were to have an influence on the other charges, the influence would be small. I prefer instead just to have a very crisp and clear definition of the electric field, to say that when we're going to measure its direction this way, we imagine nailing down all of the other charges in the system and simply putting our positive charge there in order to determine the direction of the electric field.